Hi, I'm returning to material which is in the handouts, except there are some slight modifications, a few additions I've made to clarify points that I thought weren't clear. And in this session, I'm going to be talking about modeling from a materialist standpoint. And it will lead on to material that I will use to talk about epicycles and critique neoclassical economics using the ideas that I'm presenting in this one. So, okay, what is a scientific model? The normal way that people talk about that, they talk about it in rather conceptual terms, as if a model is a set of ideas. And I'm taking a rather different sense. I'm saying that a model is something physical. It's always one physical thing which represents another. Now, we're obviously used to the idea of a model car or a model ship that a child might play with. And that is seen normally as something quite different from models in a scientific sense. And I'm going to say that no, that isn't. There is actually a continuum between those and scientific models. And in fact, some of the first scientific studies of ships, for example, by Froude, were based on constructing accurate models of ships and then towing these through tanks of water to measure the speed and the energy required to do this. So that was literally scientific modeling. It was using physical models to obtain scientific information. But I'm not just focusing on that. I'm also going to talk about how do you know whether a model is good? And in the next lecture, I'll be talking about applying this to economic theories, and particularly to critiquing neoclassical economics. And the approach I'm going to be taking is pretty computational throughout. So what's the basic modeling process? You have two things. You have the real world and you have your model of the world. And the model is obviously only an approximation of the real world. Almost invariably, the model is smaller than the real world. And if it's not smaller, it has fewer degrees of freedom than the real world. You have to be able to define what are called boundary conditions for your model from initial observations. From those boundary conditions, you then produce a set of predictions, and you compare these with other observations. In the next couple of weeks, the COP climate conference is taking place in Glasgow. And in a sense, this is a very literal version of modeling the world, because the entire process that's taking place, the entire political process that's taking place, is based on scientific models which attempt to approximate the weather and climate system of the world in order to predict what's going to happen. And they do this based on initial observations about the distribution of the landmass, the observations about atmospheric composition, observations about atmospheric density, the solar constant, etc. And from this, they then attempt to arrive at predictions and we assess the quality of these models by how good the predictions are against observations that are carried out over time. Now, usually this is thought of in terms of some scientist thinking about the physical world and constructing a conceptual model of the physical world. So here's Newton. He thinks about the centripetal forces. There's a he constructs diagrams of these centripetal forces, and he then predicts the motions, for example, of the satellites of Saturn. Now, but were these really just ideas, or are the models always machines? If you transpose to the 1960s, and instead of, or 1970s, and instead of talking about Newton, you talk about the first satellite probes that are launched, then you had computer models of the planetary dynamics, which were used to time the motor firings and send the probes to the right positions. Now, in this case, it's clear that you don't have a conceptual model. What I'm showing here is a NASA scientist in front of a 1950s or early 60s analog computer, which represented the variables that being investigated in terms of continuously varying voltages. In which case you have a dynamical system which is taken to be governed by laws, and you model the dynamical system with another dynamical system, which is a circuit with capacitors, resistors, and op amps, and one obeys the laws of the other. But even when you go back to Newton, he wasn't just thinking. When you read the Principia, there are always diagrams. It's very like reading Archimedes. It's masses of geometric diagrams, and there are arguments in terms of geometric diagrams and geometric constructions. So were these thoughts, or were they always something material, something that was produced by physical actions using physical tools? And Newton says that, in fact, it rests on geometry, and geometry rests on mechanical arts. And it is the great strength of geometry that, although it derives from mechanical arts, you can handle all sorts of other problems with it. So Newton is quite upfront about the fact that it's something mechanical that is being dealt with here, right from the start. And before Newton, there were other astronomers. There was Kepler, before him Ptolemy, and before Ptolemy, who was in I think about 200 or 300 AD, there were the Greek, ancient Greek astronomers like Hipparchus and Apollonius. And they were already constructing models of things like the moon's orbit, or not necessarily the moon's orbit, but the phenomena that were observable, like the phases of the moon and the lunar eclipses. I'm giving an example diagram here which shows the comparison between the way Apollonius and Ptolemy modeled them. Ptolemy modeled things with a deferent and equant and epicycle. You had line EC to the center of a point that the moon orbited in an epicyclic movement around it. The Apollonius model has the Earth moving around a point D and the moon moving in orbit around D. Both give the same relative predictions of angles. Turns out one is easier to model than the other. So I think I showed you this in the last lecture, just to show that even back in the 3rd century BC, astronomers were constructing physical models. The calculations were such that it was impractical to get detailed results using the set of physical models, physical tools in which the maths was defined, namely straight edges and compasses. You could do it using that, but it was much handier to make a pocket device that you could transport around, turn a handle, and get the predictions from. And what this emphasizes, that in all scientific modeling, you're taking a microcosm and emulating the macrocosm. You're creating a small physical system, which when you allow it to evolve mechanically under some source of power, in these early things, it was by turning a handle, by the early Middle Ages, it would have been by a weight descending to produce the clocks which shows the phases of the moon. I mean, this is the same basic technology which goes into the early medieval clock mechanisms, except there's no escapement mechanisms because it's not intended to be real time. It's intended you can clock it forward to find, and possibly, it's not certain, but possibly such eclipses of the moon could then be used to determine longitude, because in order to determine longitude, you need a common time frame at which point in time you can observe the angle of the moon in the sky, and that tells you you can derive the longitude from that. You can't do accurate mapping of the type that Ptolemy was doing without information on longitude. So this kind of machine worked with epicyclic gearing and could emulate the differences in rates of rotation of two different rotary systems. This is just showing the deferent and epicycle or model giving the apparent rotation of the moon and the variable angular rate you would get from that. Apollonius had a proof of the equivalence of these two models. If E is the Earth, D is the center of orbit of the eccentric model of the moon, and C the center of the epicycle. If the rotation of the epicycle is exactly the same magnitude but in the reverse direction, then CM must always be parallel to ED, and ED and EM must therefore be a parallelogram. So the path of the moon is in each case a circle centered on D, so that you get the same relative movements. Compared to Kepler's case, you're doing it in terms of an ellipse, but that is much harder to implement in terms of cogwheels. It's much harder to implement in terms of uniform circular motion. You can do epicyclic calculations with mechanical devices, but you have to cut elliptical bearings to a high degree of accuracy, which wasn't really practical in those days. Now, because that wasn't practical, astronomers had to resort to explicit digital calculation using written numbers. And when you do that, when you use explicit digital calculation, the physical dependence, the physical correlation between the model and the thing being modeled becomes less apparent. When you're dealing with an orrery or a clock, the physical comparison is obvious. They both have rotary motion, they both have cyclical patterns. When you express this in numbers and with formulae, even though you're expressing the same thing using a different technology, it becomes less evident that what you have is a physical model. Now, one thing which is worth considering is how much these astronomical models of the ancient astronomers were driven by the constraints they had in terms of the types of physical modeling they could do. If you've got a certain modeling technology, then the conceptual approach you'll take will be heavily constrained by that technology. You see shifts in the conceptual approach that people take as their modeling tools evolve. What I think is an example of that now is the kind of approach to modeling that Stephen Wolfram takes. Wolfram's approach to modeling the world wouldn't have been possible without it being possible to set up cellular automata systems as a physical device to produce the predictions that he produces. And that's a different conceptual way of thinking of the laws of nature, which comes about with a change in technology, a change in the technology available to the people who are doing the modeling. So I can't remember whether I covered this in my last lecture or not. That in 1905, there was a big revolution. There was a revolution in world affairs, and there was the first Russian Revolution. They're both produced by the same thing. They were produced by the Russians attempting to defeat Japan in a war, sending their fleet to the Sea of Japan, where it was sunk. This also produced the revolution of 1905, produced the Potemkin mutiny that is shown in Eisenstein's film, Widespread Strikes, etc. But it also produced a revolution in naval technology, some which I've talked about before, a revolution in range finding and computational technologies. Tsushima took place at a distance of about 7 kilometers. By a few years later, distances had gone up to 12 to 15 kilometers. You do a few calculations. At 15 kilometers, a projectile with a horizontal velocity of 600 meters per second, again, a realistic one, would have a 25-second time of flight. Ships were by then moving at relative speeds of maybe 25 meters a second. So during that time, they'd move 600 meters, and you need to correct for this movement in real time. So how do you do this? Well, physical analog models were what were used. This doesn't look like a computer to us now, but it is a photo of the types of computing machines that were used on ships in the early 20th century. They are like what we would now think of as drawing instruments. But the difference between a drawing instrument and a computing device is not very significant. The maths that's being attempted here is vector arithmetic, vector addition, and change of bases. This is a photograph of one of the machines. This is what you're trying to do mathematically. You've got one ship going in this direction. Suppose, for simplicity, we express it in a Cartesian coordinate system. It's got 0 horizontal velocity, a velocity southwards of 0 east-west velocity. It's got a velocity of minus 14 meters per second southwards. This one has got a velocity of 15 meters per second to the east and 3 meters per second southwards. you need to form the vector sum of those. The vector sum of A relative to B is obviously going to be 15. The velocity of B relative to A is 15 and 11. So 15 in the x direction, or it's the x direction with respect to the frame of reference of this ship, and 11 southwards. So this is in absolute coordinate systems. It just happens that the coordinates, one of the coordinate systems of this ship coincides with one of the coordinates of the north-south direction. Someone who is aiming a gun had to know the rate of change of the range and the rate of change of the angle of the other ship. With that, they could apply angular elevation deflections to compensate angular and elevation deflections to compensate for relative motion. And they used a device called a Dumaresque, which was an analog computer to do it. This is a more detailed diagram of it from the manuals that were produced for it. You took a sight along that line to the other ship. This bar here was fixed to your ship, and you slid this forward until you had your own velocity in knots. You rotated this dial to what you thought the course of the other ship was. And you then, on this ruler here, you read off what you have an estimate of how fast the other ship is going. You look through your telescope and see that it's got a bow wave, which is typical of a ship steaming at 15 knots. So you read off the 15 knot position here, and that gives you a position on this grid. You get an XY position on the grid, and that XY position on the grid tells you the rate at which the other ship's range is changing and the rate of angular deflection, the rate at which its angle is changing. Now, all of that is entirely analog. It is doing, this part of it does vector addition. You're adding two vectors, and you're doing it in a simple geometric way. And the rotation of this disk gives you a change of basis for the vector space. So I've run through it. These are the instructions which the equipment had with it. But if we express this in modern maths, you've got to extract the coordinates. So E is the vector representing one ship, O the other ship, you subtract one from the other, and R is a rotation matrix, which the rotation matrix here would be, the standard way of doing a rotation matrix is if you've got an angle theta, you construct a matrix cos theta, sine theta, and minus sine theta. You then do a multiplication of a vector by this, you get the vector in the new space, new basis space formed by the rotation of your angular coordinate system. Nowadays, you do that with maths. If I write down that formula here and feed it through a modern compiler for a what kind of processor I'm assuming here? I'm assuming an Intel P4 or something like that. The compiler generates a sequence of instructions. Now, this is hard to see that it's the same thing as the mechanical operation, but this is just a digital representation of the same thing, and it only works to the extent that I actually have a physical device. I have a Xeon processor which does the calculation. The difference is that that's a general purpose device, whereas the optical instrument was a single purpose device. Now, it's single purpose in the sense it only models ship-to-ship movements, but it acts as a physical model for a whole class of relative ship-to-ship movements and orientations. But both of them are physical systems that can be used to model other physical systems. So that is in common to them. But this is a much more general purpose model because it can model any other arbitrary physical system up to some finite limit of accuracy. But once you have configured it, it is a physical model just as much as this is a physical model. Just as the optical instrument is clearly understandable as a physical model, the maths only does, or the algebra only does what we intend it to do, to the extent that there is some physical device that will do the calculations for you. Now, I'm giving this as an example because these calculations are too fast for a human being to carry out. You can't repeatedly take that kind of sighting and either by mental arithmetic or by sheet of paper and pencil methods come up with a solution. That was why they had to have a mechanical device to do it. And nowadays you would have to have this kind of device. And since the invention of universal computers, in general, you no longer have to build special purpose mechanical models. The type of mechanical modeling of for gunnery purposes, for example, stopped being made after the 1940s. From then on, armies and air forces and navies started to use general purpose computers for it. But the important point here is a point taken by from David Deutsch's paper on the universal Turing machine and the quantum systems. He says that any finitely realizable physical system can be perfectly simulated by a universal model computing machine operating by finite means. Now, this is taken to be what's termed the strong physical Church-Turing principle. It's saying that a universal computer is equivalent to any physical system. And it's equivalent to any physical system to the extent that we believe that physical systems can be defined in terms of mathematical laws. And we can define a set of mathematical laws, and then if we have them as mathematical laws, we can always compute them on a universal computer. But Deutsch goes beyond that and shows that the possibility of having universal computing machines is itself predicated on the laws of physics. If the laws of physics were not what they were, you wouldn't be able to construct any kind of computation system, whether it be a Turing machine or a person with pencil and paper. Up until now, I've been talking about concrete models, models of the world's climate, models of the movements of ships, models of the movement of the moon. People also sometimes talk about physical laws as being a model. And these are physical laws as we now conceive of them are typically, or since Newton, have been expressed as mathematical formulae. And I think nowadays it's better to think of these physical laws as software that have been proven in practice to be reliable for the construction of models. When calculations were done by hand, it was just less evident now than it is. These are general purpose software. Now let's look at it from the standpoint of information theory. What your model's got to do is generate testable predictions. And if it makes no testable predictions, it's useless. It doesn't tell you anything. Secondly, you want your model to be as simple as possible. I mean, this is Occam's razor, that entities shouldn't be multiplied without cause. Newton makes the same argument. And it's got to be an operational model. It cannot have undefined variables, because if it does have undefined variables, it's not computable. Now, these may seem very obvious points, but we'll see when you come to neoclassical economics that these are disregarded to a ridiculous extent. And yet neoclassical economics is still treated as if it was a serious subject. Okay, now, when I was talking about Marx, I said that one of the things Marx was concerned about was information economy. And on this, you're certainly right. And he was just repeating what Newton and Leibniz had said at that point. But we can now formulate this more precisely. The use of a model is something which, given some input data, generates both the original input data plus a set of predictions. It doesn't destroy the input data. After you run the model, you have both the predictions and the input data. Now, I'm going to use the word elegant in the sense that the mathematical philosopher Chaitin uses it. He says, for a model to be elegant, you want to maximize its information yield. And this says that the information yield is the information content of the predictions divided by the information content of the model. You want to produce as much information in your predictions with the minimum information in the model. If you have more information in the model than the predictions, then it's worse than useless. It's throwing information away. For it to be useful, we want to do more than that. We want to maximize the mutual information between the predictions and the observed system. That is to say, the model has got to be right. If the model says one thing about the world, the same thing must happen about the world. If the model says it's going to be raining today at 5 o'clock, you want it actually to be raining today at 5 o'clock. How do you work out mutual information? Well, you work out the mutual information in terms of the entropy of the predictions minus the entropy of the predictions given the observations, where H means entropy, P bar O means predictions given the observations. And you want to maximize that whilst minimizing the information content of the model. That's to say, you've got to avoid models which contain lots of internal information, because in the worst case, such a model just tabulates the observations. It tabulates past observations. Why do you use entropy? Well, because entropy would appear to be something to do with the efficiency of steam engines and heat and stuff like that. But a key discovery of the 20th century was how the 19th century concept of entropy derived from the study of steam engines turns out to be relevant for the study of information. I was talking about this before in the context of Marx. There was the materialist theory of heat, which there was a substance called caloric, and I said that Dalton supported this view. The mechanistic theory was that it was the motion of gases. And by the 19th century, the mechanistic theory had replaced the old materialist one. So let's see what is information, how does it relate to entropy, as discussed first by the 19th century thinkers. What? Clouds flow from a colder to a hotter body. But Maxwell argued that it was only lack of information. Is his famous Maxwell's demon problem. He says, suppose you have a gas initially in equilibrium, divided by a partition. You have a demon who opens the door only to let fast molecules move from A to B and slow molecules to move from B to A. Now, that doesn't use up any energy, because you can say that you can have an elastic spring which closes and reopens the door, and he's only opening and closing it to let things through. Now, this may seem sort of far-fetched, but we now know that there are pores on the surface of cells which open and close to let calcium and potassium ions move through. So the idea of very small devices which let through individual molecules, though it wasn't known of in Maxwell's time, it's not unrealistic. What happens after a while is you get all the slow molecules on the left-hand side and the fast ones on the right-hand side. So you've reversed heat flow. You've had heat, you've got heat flowing from a colder to a hotter process, and just information about whether this from the cold area, so you can run power from. Materialist model in the modern sense of it being an atomist one. And foundation in terms of an integral over molecular phase space, where there's, this is his S formula, K is Boltzmann's constant, the F is a function which denotes a volume in 6-dimensional phase space and counts the number of molecules present in it, and he expresses an integral of F, where, as I say, it's 6-dimensional phase space, where phase space is position x, y, z, velocities dx, dy, dz. Now, in the 1940s, Shannon comes up with a formula for measuring the information content of data being sent down telegraph lines. Similar in that it contains a probability here, a log, in this case he takes log to the base 2 instead of natural logs, and the log of the probability. So it's essentially the same thing. He says the mean information content of an ensemble of messages is obtained by weighing the probability of each message by the probability, weighing the log of the probability of each message by its own probability. And he shows that no encoding of messages, zeros and ones, could be shorter than this. And that's essentially the same as Boltzmann's entropy formula. So from Shannon onwards, in 1948, we've known that information and entropy are actually the same thing, in the sense that they have basically the same formula. One is done with a summation on a discrete space. In principle, Boltzmann defines it as, but in practice, when anyone was working at, they would use some kind of discretization. It has to have two potential wells. If this is energy levels, you have two potential wells with a barrier in between. One of the potential wells stores a 0, the other one stores a 1. So that is a model of any at a high level of abstraction. That's a description of any digital memory system or binary digital memory system. And he's able to argue from this that any kind of information heat loss, because you need a certain energy to go over this, and you need to put energy into the system to cause it to move from a 0 to a 1. His formula is that the heat loss will be the natural log of 2 times Boltzmann's constant times temperature. So this is just Boltzmann's constant comes in, and you get an actual figure for the amount of heat, the minimal amount of heat that a digital information system can produce per bit of data that it processes. This is a very small, very few computing devices are close to the Landauer limit, but it does show that there is a fundamental physical limit to how low the power consumption of any device that is processing information, whether it's human brains or digital computers or cellular systems. Any system that's processing information cannot do it with less heat loss than log 2 kT per bit. T is obviously the temperature which is occurring. Now, let's go back to what I was trying to maximize the mutual information of predictions and observations, and that's given by the entropy of the predictions minus the entry of the predictions given the observations, where the entropy is the uncertainty. Now, how do you compute that? Let's continue. You have a continuous model where we're talking about whether it's going to rain, and this is over the course of the day. This is the probability that it's going to rain according to the prediction, or let's not say the probability of rain, the intensity of rain predicted. And you have rain gauges, and this is the actual rain gauge. So you want to say, how good is that as a model? Well, you can compute the entropy calculations on a rain gauge with multiple gradations, but it's a little harder to conceptualize that. So I'm going to give the simplest possible one, where you have, from most people's point of view, that's enough. You want to know, is it going to be raining and I can go out without a raincoat, or will it be raining and will I need my raincoat and umbrella? So you can treat that as a binary prediction. And suppose this bottom one indicates periods when it actually is raining. It's raining from just after 1 o'clock to just after 1:30. Then we get a spike of rain at about 2:30, which runs till about 10 to 3. And then it starts raining again shortly after 4 o'clock. Suppose I have a weather forecast which makes these predictions, these points here. How do I compute the entropy of the rain given the prediction? Well, it's actually very simple. You compute the XOR of the two. of wrong predictions. And you can then apply Shannon's formula to see what is the entropy of that. That is to say, how compressible is that? Because what you'll get is that there'll be long periods when the predictions are right and just occasional blips when the prediction is wrong. And in principle, if you have any bit stream which has a non-equal probability of zeros and ones, then you can apply a compression algorithm to it and reduce the amount of information. That reduced amount of information is the entropy of one given the other. The next thing is you need to be able to quantify the amount of information in your model itself. We've talked about the entropy of the predictions versus the observations and shown that you can apply Shannon's method to extract that. Chaitin talks about the information stream of a string of digits. And we know that any computer program can be represented as a string of digits. And in general, he says that the information content of a string of digits is bounded below by the length of the shortest possible program. Any text or picture can be represented by binary digits. This is a very general principle. Now, if you look at the model, it's going to be made up of two basic things: a basic structure or formula, which you can read that off and say, okay, we assign a byte for every symbol in the formula, and a set of auxiliary parameters or constants that have to be provided. And each of these is given an information measure to write it down, and the parameters are, a law is a rule by which models can be constructed. And in general, you can say something is a law if it's a model construction method that has a simple, elegant formulation and few parameters, and it makes excellent predictions in an apparently unlimited number of cases. In the next lecture, I'll be applying these information theoretic principles of modeling to analyze the foundations of neoclassical economics and show the Ptolemaic epicycle theory. Okay, I think that I've gone through this slightly fast, but I'm still going to stop and